All right, this is section 11.6 about parametric equations and plane curves. All right, so let's take a look at what these parametric equations are. So let f and g be functions of t over an interval I. Then the set of points defined by x, y equals f of t, g of t is called a plane curve. Notice that just says x is a function of some variable and y is a function of that variable also. Kind of like, we've seen this before, this is like saying x, y equals cosine t, comma sine t, if you remember that. All right. The two x equals f of t and y equals g of t are called parametric equations of the curve, and t is called a parameter. All right, so to graph with a parametric equation, pick values of t in the interval I, and find the values of x and y, and then plot the points on the plane. Okay, so we'll do that for that one. We'll do it in class for the first example, letter C. All right, let's look at some of the other ones. So to eliminate the parameter, that means having parametric equations and writing in rectangular form. That means going a little bit kind of backwards, having f of t and g of t and writing it in terms of x and y. But there'll be equations. All right, so some pointers. So to eliminate the parameter, we can solve for t or an expression involving t in one equation. Notice it can be t itself or an expression involving t. Substitute in the other equation, identify the domain restrictions on the resulting rectangular equation, and we'll see how that's done. The orientation of the curve indicates how or what order points on the curve get filled in as t increases. To see the orientation, we can just pick two values of t and just see as t increases which how the points are moving, right, from which point to which other point. Okay, all right. Recall also the Pythagorean identities, like cosine squared plus sine squared equals 1, cotangent squared plus 1 equals cosecant squared, tangent squared plus 1 equals secant squared. And remember, you can rewrite these also, right? Like this one, we can write secant squared minus tangent squared equals 1. All right, let's see an example of this. So let's take a look at the first one. And we'll do the first one, I'll do the first one here, and we'll do the second one in class. And I know that, maybe you won't know how to do it. We'll discuss it a little bit. All right, so the first one, it says for each A, eliminate the parameter and write in rectangular coordinates, and then B, sketch the curve and indicate its orientation. Okay, so first I want to solve for t. Okay, so it'll be harder to solve for t on this one, although I can. But I'm going to start over here. So this, I'm going to solve for t, so this will be y plus 1 equals t. And then that y plus 1 for t, I'm going to replace it in the other equation. So this will be x equals the square root of, t is y plus 1, and then minus 1. And so that'll be x equals the square root of y. And if I square both sides, I get something that's a little bit more familiar. X squared equals y. Yeah. Notice, by the way, that if we look at this up here, x equals square root of t minus 1, because it's a square root, then we know that x has to be greater than or equal to 0, because the square root has to be greater than or equal to 0. So that'll help us with the domain of our function that we've found. Okay, y equals x squared, which I think we're all familiar with. All right, let's take a look at. We'll leave number 2 for class. Let's take a look at part 3, writing parametric equations to represent a curve. So to write a parametric equation from rectangular, pick a convenient definition, aka replacement for x, like for example x equals t, and then substitute in the parametric equation for y. That is to say, in the equation that we have for y. All right, so let's do one of these. Let's do, so we're going to write parametric equations for the curve defined by y equals 2x minus 3 with the given definition for x. Now, we know what y equals 2x minus 3 looks like, right? It's a line with slope 2 and y-intercept negative 3. So if we replace x with t over 5, notice that's, when we say x equals t over 5, that's like saying this one over here, x equals f of t. Right? So f of t is t over 5. And then y, in terms of t, it'll be g of t. So we just replace the x with t over 5. So y will be 2 t over 5 minus 3. Okay? And then we'll see what that looks like. So we know what that line looks like, and then maybe we can graph these parametric equations to see that they match that same equation. Okay? And we can do the same thing with the other ones. Right? So you're going to do the same thing that I just did for these other ones. Okay? Doesn't sound too hard, right? All right, let's try number 2. So number 2, you know what? Let's leave that one for class. So first we'll find the rectangular equation for the line, and then we'll do what we just did on letter C. Okay. All right. All right. We'll leave the rest of that for class, and then I think we'll leave this last one for class. So this one, we're actually given parametric equations for x and y. This is projectile motion. That means like throwing a ball or hitting a ball in its trajectory, or some other projectile. Okay, so we'll look at this one in class entirely. All right, let me go back and let's do one more of these since there's a few of them. So let's say we take x equals negative 4t. So y then will be 2 times negative 4t, right? Because x is negative 4t minus 3. This will be y equals negative 8t minus 3. Now remember, these two parametric equations are still replacing the the same rectangular equation. So these two different sets of parametric equations will graph out the same line. All right. Oh, on this one I forgot to do the orientation. So let's do that now here also. So the orientation for x squared. So let's see. So let's see which. So we know what this looks like, right? So we know it's a half a parabola because it's for x greater or equal to 0. Half a parabola. So it's going to go kind of like that, right? All right, and then we want to put some arrows to see in which direction the points are getting filled in. So if we pick t equals 0, x is square root of negative 1. Well, that's not gonna work. All right, so let's pick. So t has to be greater than or equal to 1 also. Okay, so that's a good thing to see. So t has to be greater or equal to 1, right? So that our square root can be defined. Okay, so at t equals 1, x is 0, and y is 0. At t equals 2, x is square root of 1, which is 1, y is 1. So the graph is getting filled in that direction, right? We just saw right now when we picked t equals 0, it started here. For t equals 1, it was over here, right? So as t goes up, it's getting filled in that direction. Okay, and we'll do the same thing with number 2 here. Fill in those little arrows to see which direction it's going, and we'll graph these just so we can see, just to make sure we know that that we're headed in the right direction. Okay, so I'm going to stop there for this section. All right, not a whole lot of new stuff, or maybe it is. I don't know. All right, so that'll be the video for section 11.6.